Let's continue with unsupervised classification. So last time I introduced the algorithm of ISO data unsupervised classification. And today in this video, I'm going to start this video with an example here. Okay, so we have several scatter plots here. The first one is 10 classes after the first iteration of ISO data. So you can say we have in general two hues here. Hue 1 is a green, hue 2 is pink. But within each hue, there are different saturations. So two hues and several saturations together, okay, they are used saturations and hues. They're used here to represent how many classes? From 1 to 10, 10 classes, okay? First four classes, they are portrayed by green. The rest classes, they're addressed by pink. Of course, green with different saturations, pink with different saturations. And this is the result. This is a scatter plot after the second iteration, third iteration, 4 iterations, 5 iterations. You can say the spatial distribution of these classes is changing after each iteration. So at the very beginning, they are aligned on a straight line, right? From class 1, class 2, class 3, class 4, class 5, until class 10. And after 10 iterations, this is the spatial distribution of them. 1, 2, 3, 4. So first 4 classes, they are right here. Then 5, 6, 7, 8, 9, 10. If you compare this scatter plot after 10 iterations and the one after the first iteration, you will see that spatial distribution of these classes within this feature space changed a lot. And after 20 iterations, this is the result. This is the result. Okay. So you can say from first iteration to 20th iteration, you can say all these classes, they have been accurately reclassified again and again and again after 20 iterations, or you can consider this 20 iterations as 20 reclassification based on the first classification. This is a change from 1 to 10, and here is the result. Here is the result. Although there is no numbers for different classes in this scatter plot, you can simply compare this one with the first one. Okay, so here let's just connect this result with the actual picture. So this is the actual remote sensing image for South Carolina, right? North Inlet, I think that's a small city or town in South Carolina. But yeah, this is a image. This is a scatter plot of ISO data after 10 iterations. So like I mentioned before, as a result of unsupervised classification, each class is simply a number. The software doesn't know which class is exactly what land cover in the real world. So you have to use your own knowledge as a remote sensing analyst, as a GIS analyst, to assign specific land cover or land use to each class. So this is a result. Class 1 is water. So this is class 1. So class 2, wetland. It makes sense, right? Wetland is very close to water body, okay? Class 3 is also wetland, okay? There is no further explanation, but it's possible that there are different types of wetland, but it's also possible that class 2 and 3, they're just too close to each other. It's not necessary to differentiate them. So according to the analyst's decision, we should combine class 2 and class 3 and consider both of them as wetland, or simply say we have 2 and 3 combined as one class, wetland. And I think that is the fact for this specific image, because class 2 and class 3, they're using exactly the same color in this thematic map. Okay, so class 4 is for roof asphalt. It's a part of impervious surfaces. Class 5 forest, typical vegetation. Class 6, again, you can say class 6 is also wetland for some reason. Okay, for some reason, but class 6 is right here, right, in this scatter plot after 10 iterations. So class 2 and 3, they are wetland. Class 3 is also wetland. In the feature space, you can see that class 6 and 3 and 2, they're not very close to each other. Class 4 is even closer to class 2 and 3 compared to class 6. But here you can say the importance of the knowledge from the analyst, especially for unsupervised classification. The analyst, for some reason, decided that class 6 is also wetland instead of something else. And on the other hand, although class 4 and class 3, they're very close to each other in the scatter plot, in this feature space, class 4 is very different from class 3, because class 4 is obviously man-made material, it's roof asphalt. Class 3 is wetland. So when we're looking at this scatter plot, do not think that all those classes close to each other should be similar to each other in terms of the land cover in the real world. Here is a very good example. Class 3, class 4, they're very close in the feature space, but they're actually very different. Class 3 is natural land, wetland, right, with a lot of water and vegetation. Class 4 is very close to class 3, but it's roof asphalt. And on the other hand, class 3 and 6, they are not very close to each other in this feature space, but the analysts decided to assign class 6 as wetland, just like class 3. Okay, so you can see here your experience as a remote sensing analyst, prior knowledge you have on your hand is they're very important when we're talking about unsupervised classification, because you need to use your experience, use your the knowledge you have, the information you have to decide which class is what in the real world. Okay, I think that's the most important part I want to address from this slide. Okay, here is the original image. Here is the classification result. Okay, and here is the thematic map after ISO data. Actually, let's go back. This is the scatter plot after 10 iterations, right? So we also have another image here for the classification after 20 iterations. So 1, 2, 3, no big change, right? If you compare this scatter plot after 10 iterations and the one after 20 iterations, the relative positions or the locations of class 1, 2, 3, 4, class 1, 2, it's not accurate. Let's just say 1, 2, 3, 4. Yeah, class 6 is further away. Some part of class 6, very close to this location, they are assigned green here. Okay, yeah. So, yeah, I think this whole figure here is from the textbook. I think it's more appropriate to use the scatter plot after 20 iterations here. Okay, because after 20 iterations, some part of class 6 around here belongs to class 3 and a little bit of 4 after 20 iterations. So maybe it's better to use the figure after 20 iterations. But anyway, this is a figure from the book. But what I said is still effective. When we're talking about unsupervised classification, it's crucial to make sure that the analyst here is, I mean, if possible, is experienced, and there should be some useful information, knowledge in his or her hands to decide which class is what. Okay, that's for ISO data. So next type of classification I want to introduce here very generally is called object-based classification. So classification units are not pixels anymore. They are image objects. Okay, and what is image objects? They are defined as individual areas. Be careful here, not pixels. Individual areas with shape and spectral homogeneity, which means that we need to use the knowledge of a lot of things. For example, the shape of something, the shape of an object in your image, or the spectral characteristics of objects in your image to decide how to create image objects in your image before carrying out object-based classification. So which one may recognize as segments or patches in the landscape ecology literature. Okay, so these objects can also be called as segments or patches. Okay, if we are talking about landscape ecology, and remote sensing images, they are widely used in landscape ecology. Okay, to decide or to address spatial configuration and spatial composition. Okay, but that's another story. So objects don't have to be derived from just image data, but can also be developed from any spatial distributed variable. So let's see some examples here. So here is a true color image of a very typical urbanized area. So we have a park here with grass, tree canopies, and there is a small plaza here. And at the bottom right corner of this image, we have a very typical building configuration here, right? It's just like Derby Hall. There is a well in the center of this building, and we have four sides of this square, and this each side is a part of the building, right? On the left side we have a road and several, I think, buses, right? They're very long vehicles, right? And other buildings here. So in order to carry out object-based classification for this image, we need to use specific methods. They are listed here, commonly used ones, to divide the whole image into small patches like this. Okay, so all those yellow boundaries, they are used to identify small patches or segments or objects. Let's just call them patches. And you can say each patch is based on something. For example, this building at the bottom right corner of this image is divided into patches, right? The small plaza in the center of the building is divided into 1, 2, 3, 4, 5, several small patches based on something. What do you think that something is? Reflectance is the most direct, the most direct one, right? So obviously, if you compare the color, the reflectance of this plaza to the surrounding buildings, there the reflectance is different, right? And the brightness value is also different in this true color image. So it's not that hard to just divide this plaza into small patches depending on brightness values. And obviously, the roof of this building here has a different color. It's basically orange, right? You can also use that to divide this whole building roof into small patches. Okay, and we also have a lot of patches for shadows, right? This is the shadow of the building, and we have several small patches for shadow. And the color of shadow and the highly dense vegetation is very similar. Shadow is black, and you can see that the tree canopy here is dark green. And the boundary between the shadow and the canopy is pretty hard to recognize. You cannot tell this part, if this part is shadow or vegetation. So you can see here for this specific location, right? This is this, let me use a pen here. So this is generate the boundary of this tree canopy and its shadow. Its relative location here, it should be around here, right? That's a tree canopy and its shadow. So you can say that this whole area is divided into small patches. And of course, some of them, they are not absolutely accurate. Actually, it's not possible to 100% perfectly divide a specific area into small patches, and each patch is accurately representing its real world land cover type. But here we have different methods to do that. Okay. So here is another example using different scale factors to divide the whole area into small patches. So here, for example, this is an image, right? When we're talking about segmentation scale 10, so this is a result. We have very small, detailed patches here, right? A lot of them. And when we change the scale factor to 20, less patches can be found here in the same image. If you increase this value to 30 or even 40, you can say larger and larger patches are used, which means less and less patches are employed, okay, are produced. So you say which segmentation scale factor I should use? Well, there is no correct answer again. So you have to decide the accuracy of your classification. If you need a very detailed classification, then of course you should use more patches, because the software does not divide the whole image into patches randomly. The software must follow some principles. Like I said, the shape, the texture, the spectral characteristics are from different bands, right? So you have to try different configurations, and you have to have some knowledge of the area covered by the image. You have to consider the specific requirement of your application, of your research, and combine all this together and try multiple times to decide which classification method is better, which scale factor here is better. Okay, so here is just an example. So that's all I want to say about object based classification. It's a relatively new method. It's not that widely used compared to traditionally used supervised classification and unsupervised classification. But if you are interested in object-based classification, I think uh, I I don't think I don't think Envy and ERDAS, which is the one you are using in your lab, I don't think they have object-based classification last time I checked, but that was like 2 or 3 years ago when I did my PhD dissertation. Today, maybe there is update about this part. I'm not quite sure about that, but there is another remote sensing software is called eCognition. I think that's the name. It is very famous for object-based classification. Okay, so next part, the last part of this lecture, I want to talk a little bit about accuracy assessment of classifications. So this step of classification is not exclusive to a specific category of classification or a specific method of classification. As long as you do classification, you need accuracy assessment when you get the result. So it is an important element of image classification processes. It is conducted by comparing the classified images with the reference data, which is believed to be accurate. So here, since we're comparing two things, there must be a baseline, right? That baseline in this specific scenario is called reference data. For example, data published by local government. Okay, land cover map published by local government. Or if you still remember NLCD data published by US government, they are usually considered as a data that can be trusted, or we usually consider them as ground truth. Okay, for a specific block, if NLCD tells you that this block is fully occupied by vegetation, which means that block is a city park, right? Then you should consider that as the ground truth. On the other hand, according to your own classification result, that block is urbanized, is covered not by vegetation. Instead, it's a parking lot, it's covered by asphalt. Then you should consider your own result false, okay? Because it's totally different from the reference data. So when we're talking about accuracy assessment, we compare your classification results with reference data. Okay, and in order to carry out accuracy assessment, we need to sample. We need to sample a part. Sorry, let me turn this off first. We need to sample a part of your image, of your thematic map, of your classification result to compare to the reference data, because it's not necessary to just compare the whole image to the reference data. So we need to decide the size of sample, how many pixels you want for accuracy assessment, and a sampling design. What's the scheme you are going to use to choose all those sample pixels? That's a problem. That's a problem of statistics. And also you need to create something called error matrix to compare your results with your results represented by samples, of course, with reference data. And you need to use accuracy measures to quantify the accuracy. Okay, let's just go through these four components. Okay, how many samples or how many pixels are needed in accuracy assessment? So there is no laws or specific requirements for that. So we have a rule of thumb. Collect a minimum of 50 samples for each class. So each sample is a pixel, right? So increase the sample size to 75 or 100 if there are more than 10 classes or the area of certain classes is extremely large. So this is here for you to make sure that your samples, your sampled pixels, let's just use samples here, okay? Each sample is a pixel. To make sure your samples, they're good enough to represent all those classes. Okay. So usually for each class we have 50 samples. If you have a lot of classes and one class or many classes, they are covering large areas, then you should increase your sample size. Okay, and the second step, sampling design. How to find out those samples? Random sampling, that's the most commonly used one, very straightforward, right? And we have other methods here, systematic, stratified random, stratified systematic, and cluster sampling. Let me use several figures to show you the difference of them. So this is random sampling. So of course, this rectangle here is used to address your image, right? If you're simply using random sampling, you just randomly pick some pixels within this range, right? So each black dot here is a sample. You can consider each dot here as a pixel, right? So this is random sampling. That's it. Randomly generate some x values and some y values and just combine them. You have a bunch of pairs of coordinates, right? And you have those sample points. And then we have something called systematic sampling, which means that we regularly deploy sample points across the whole area, just like this, right? In this image, we have valley, we have range, so obviously it's a mountainous area, but we don't do random sampling anymore. We assign a specific distance between samples, right? That will make sure that all samples within this image, they are regularly distributed, just like this matrix of black dots. Again, each black dot here is a sample. So you can say they are regularly assigned, and this matrix of dots covers the whole area. Okay, and a disadvantage of systematic sampling is that because the distance between samples is settled, so sometimes some land cover type may not be sampled eventually. So here, this image here is very convenient because you can see that this valley here is well sampled by 4 dots. Right? This range here is conveniently and perfectly sampled by 1, 2, 3, 4, 5 pixels. Perfect. Another value is well sampled by 1, 2, 3, 4, 5. Another 5 samples. The last range here is perfectly sampled by 1, 2, 3, 4, 4 samples. That is so good. Yeah, very good. But in your research, in your application, if you're using systematic sampling and a specific land cover type only covers a very limited area within your image, and you are using some systematic sampling, it's very likely that that small land cover type will not be sampled because you are regularly distributing all samples within the space. For example, let me give you an example here. Let me say, yeah, for example, here we have a small water body right here. It's very small. And if that's the case, no sample is within this area, which means that according to your sampling method, there is no water body in your image. That is not true because there is water body. You simply did not sample it. Okay, so now you can say how convenient this image, this specific figure is. All valleys and ranges, they are well sampled by this method. So when you are doing systematic sampling, be very careful with the question that are these samples representing all land cover types very well in the area? If the answer is no, do not use this method, okay? Here is a very extreme example here, right? I draw this polygon and use it to represent a very small water body within this area, okay? So this is water body. And according to your systematic sampling, it is not sampled. And that is something you do not want to face when you're talking about classification and accuracy assessment. Okay, systematic sampling. So the next method is called stratified random sampling. If we are not talking about remote sensing, which means that there is no spatial context, you have a group of data. A stratified random sampling means that you have to divide your whole data set into small groups and maybe randomly sampling some observations from each small group. And each group can be considered as a stratum. But since here we're talking about remote sensing, we have a spatial context, right? So again, this rectangle here is an image. It's a very complex one. There are 4 classes here, and we can consider each class as a stratum. Okay, we have 4 classes here, and class 2 is for corn, class 4 is for forest. For class 1 and 3, I'm not sure, but let's just consider that we have 4 classes here. So stratified random sampling for remote sensing imagery means that we're going to classify your image using some method. Classification is one method, right? For example, we have 4 classes here, right? Or you can use specific arbitrary boundaries to divide your whole image into small areas or regions. In that case, each region is a stratum. Here, for this specific image, each class is a stratum. And when you have stratified your imagery, we want to sample from each stratum. What's the advantage of that? It makes sure that each stratum is well represented by your samples. For example, for stratum 4 forest, right? And you can say this black area is forest, and a forest also exists in cornfield, right? Here we have 2 black patches, and also in stratum 1, I'm not sure the land cover type here, but you can say that within each stratum, we sample some points, we sample some pixels. It makes sure that all stratums, they are well represented by your samples. That's stratified random sampling, okay? And if we compare a combined stratified random sampling and a systematic sampling, this is the result. It has a very long name. We call it stratified systematic unaligned sampling. So what is stratified? Those small cells, they are representing the stratified part of this method. The whole image is divided into small regions, and each one can be considered as a stratum. That's a stratified. What is systematic part of this sampling method? Within each what? Within each stratum, there is a sample point, which means that at stratum level, all the sample points, they are regularly distributed, because you can say that within each stratum, there is only one sample. And what is the unaligned part of this sampling method? You can say that all the samples in all stratums, there is no, how can I say, there is no repeated location for each sample in all those stratum, which means that, for example, we have sample A, B, C, D, E, F, G. They are all in different locations in terms of a stratum. Okay, for example, A is right here, a little bit to the upper right of the center of the stratum. B is bottom right, okay, or to the center of this stratum. E again is different in terms of its location within that stratum. So although we have regularly distributed stratums within this space, the sample point, the sample in each stratum has a unique location. Okay, so that's the unaligned part. It makes sure that all those sample points, for them at least, they are not regularly distributed within each, we should not say within each stratum, within this whole space, right? If we ignore all those cells here, we can say that it's safe to say that all these black dots, they are not regularly distributed within this space, right? So that's the unaligned part of the sampling method. So it's a combination of stratified method and systematic method, and we make sure that all the samples, they are not regularly distributed within the space. And the last one is called cluster sampling. Sometimes I usually consider cluster sampling is a subcategory of stratified random sampling. Why? Because in order to do cluster sampling, you have to identify some clusters first, and then you pick samples from each cluster. For example, we have several clusters of dots here, right? All these dots, again, they are samples. But where are the clusters? You can consider these samples themselves forming several clusters, 4 clusters. But the actual situation is that here is a cluster. Here is another cluster, the 3rd cluster, the 4th cluster. These clusters, they will not portrayed in this image, but actually that's the first step of clustering sampling. You have to find out some clusters, and then based on these clusters, you sample. So why do I consider a cluster sampling is another type of stratified random sampling? Because you can say each cluster here can be considered as a varied stratum, right? And you just sample within each stratum. So what's the difference here? The difference is that when we're talking about stratified random sampling, usually there should be no gap between stratum, which means that this image should be fully occupied by stratums. But here in cluster sampling, you don't have to do that. So here we have 4 clusters. We are only interested in these 4 regions in your image. We'll just do sampling based on these clusters. As for the rest, right? The rest, empty space of this image, just ignore them. Okay, so that's the reason why I'm saying that cluster sampling is a verified stratified random sampling. But yeah, again, this is just my personal thought. You don't have to follow this logic, but what you need to know is all these methods, okay? All these methods. Cluster sampling, is there an option to erase all? Yeah. Stratified random sampling, stratified systematic, unaligned, and cluster. And what's the first two? Systematic and random sampling. Okay, and again, like I said, these methods, they are statistical methods. And sampling is always a problem when you are talking about research and application. As long as you're facing a group of observations and the number of observations is just large enough, you cannot examine all of them. You always need to do sampling, okay? And next, create error matrix. Sounds high-end term, error matrix. It's not that complex. I'll show you. It's also called contingency table or confusion matrix. It's just like this. It's very small because we only have 3 classes here, and it's very easy to calculate because the numbers here are very small. Okay, but this is just good enough. This is just good enough to give you an impression about the concept of error matrix. So we have columns. We have 3 columns, A, B, C, and 3 rows. And all those columns, column A, column B, column C, they are for ground truth classes. Okay, and for 3 rows, they are for thematic map classes. Okay, still for A, B, three classes, A, B, C, 3 classes, right? So, oh, sorry. What does it mean? Let's check this table. So for column A, we have intersection between column A and row A, column A and row B, column A and row C. What does it mean? So it means that there are 35 pixels in your image are classified as class A. And in real world, they are correctly classified. In real world, these 35 pixels, they are class A. So 35 at the intersection of column A and row A means that 35 pixels, they are correctly classified. So they are classified as A in image, they are class A in real world. These 35 pixels, they're good. So you understand the logic here? What does 10 mean? Which means that 10 pixels in the image are classified as what? Class B, but they should be class A. Okay, so 5 pixels in real world, they are class A, but in the image, they are wrongly classified to class C. So what's the meaning of this 50? It means that within this area, 50 pixels belong to class A. That is ground truth. So 50 pixels here is the ground truth for class A in the real world, but only 35 of them were correctly classified to class A according to your classification method. 10 pixels were wrongly classified to class B. 5 pixels were wrongly classified to class C. So I finished the explanation of column A. So you can follow this logic to explain column B and column C. Okay, so what's the meaning for each row? Let's explain each row here. So for row A, 35 pixels of class A, they actually belong to class A in real world. So 35 pixels, they're good. 2 pixels in your classified image belong to class A, but that is not correct. These 2 pixels, they should belong to class B. Okay, similarly for these 2 pixels classified to class A in your thematic map, but they are actually a part of class C in the real world. So 39, what's the meaning of 39? It means that 39 pixels in your image, they were classified as class A, but only 35 of them, they were correctly classified. Another 2 of them, they should not belong to class A because they are class B. Another 2, they should belong to class C, but they were wrongly classified to class A. So that's the meaning for row A. So following the same logic, you can explain row B and row C. And this table here is called an error matrix, confusion matrix, or contingency table. Okay. So what's the meaning of this 136? It means the total number of pixels in your image. Of course, it equals the pixel in the real world. So if you add up 50, 40, and 46 is 136, which means that in real world, there are 136 pixels. If you add up 39, 50, 47, it's still 136. It means that in your classified thematic map, there are 136 pixels, that's for sure, right? Okay, so the diagonal here is important. Numbers or observations along diagonal of this table, they are correctly classified pixels, right? Okay, so based on this table, based on this matrix, we can calculate overall accuracy, user's accuracy, and producer's accuracy. So overall accuracy, the percentage of correctly classified pixels. It is calculated by dividing the number of correct pixels by number of all pixels in the test sample set or your whole image. So where are correctly classified pixels? Along diagonal, right? 35 plus 37 plus 41. That's the number of pixels that were correctly classified, divided by the total number of pixels. What's that? 136. So overall accuracy, 35 plus 37 plus 41. The sum is divided by 136. You get a percentage or a decimal 0.83 or 83%. That's the overall accuracy of your classification. That's a pretty good one. Okay, not very high, like 90 or 93 or 94, 95, but it's okay. It's acceptable, but it's only acceptable. Okay, it's not very accurate. That's overall accuracy. And user's accuracy, it is calculated by dividing the number of correct pixels for a class by the total pixels assigned to that class. So it's for your users to consider. Okay, so for class A, the user's accuracy is the ratio between 35 and 39, which means that after your classification, okay, I'm the user, you did the classification, you provided me this data. So what's your accuracy? That's accuracy I care about. I'm the user, right? So I care about the accuracy of your classification method. How to do that for each class. For class A, you said that 39 pixels belong to class A. But the fact is that only 35 of them belong to A. So what's your percentage of correctness? So 35 divided by 39, that's 90%. So what does this 90% mean? It means that the classification method you used can very well classify pixels for class A, because for class A, 90% of the pixels are correct in your thematic map. Similarly, for class B, the percentage is 74. So 74%. Compared to class A, your performance is not that good. It's worse than class A, or you can say it's not as good as class A, because the method you used produced a 90% accuracy for class A, but only 74 for class B. So you can say that even for the same classification method, depending on the image you are using, depending on a specific classification of a specific image, its performance for different classes could vary. Okay, if you are using another part of the image to do the same thing, or if you are using the same method on a totally different image, this user's accuracy for different classes could change. Okay, it all depends on your specific error matrix. So last one, producer's accuracy. It is calculated by dividing the number of correct pixels for a class by the total pixels assigned to that class. What does it mean? It means this. We care columns here. We care about columns here. So what does it mean? It means that for class A, there should be 50 pixels. That's ground truth. But your method only, your classification only gives me 35 of them. The rest 15 were wrongly classified. So for class A, the producer's accuracy is the ratio between 35 and 50. and the result is 70%. Okay, so for users accuracy, we care about each row here because it's based on the thematic map. The thematic map is something a user would care. Okay, I want to use this thematic map to retrieve information to make decisions. I'm a user. On the other hand, producer's accuracy is column-based. What a producer cares is that how many pixels have been identified for each ground truth class. Because, for example, for A, there should be 50 pixels identified by my classification method, but it only identified 35 of them. The rest 15, they were wrongly classified. That is not something I want. So I calculate the ratio between 35 and 50 to get a percentage of 70. Okay, so that's producer's accuracy. Okay, that's all I want to introduce in this lecture, right? We went through the concepts needed for classification, and we discussed different types of classification methods, right? Supervised, unsupervised, object-based. And then the third part of this lecture was about accuracy assessment. It's something you always want to do after finishing a classification. Okay. Okay. Next week there will be the only exam of this class. I will post an announcement in Carmen to address the format, the content of the exam. Okay. So after this video, please go to your Carmen website and check that announcement for the information of the exam. Okay, thank you very much. Okay, I will see you after the exam. And do not forget your course project proposal is also due on the exam day. Okay, so do not forget to finish it. Thank you.